So thanks for all the questions, because all of those were absolutely the right questions, and I hope to address some of them. So those were more, like most of the questions were asked were advanced. That's where I'm going to head now. And because there are, well, for various reasons, I decided to do this last lecture more or less on slides. It'll have a little bit of a flavor of a seminar, but I hope so I essentially solved the problem I set out to solve with all the formulas written down. If you're a student and you want to work through it, all the information should be there. Otherwise, you're welcome to email me. So here I want to sort of talk about things which we may not understand completely, and so on. So that's why I want to switch to this mode. Okay. All right. So I want to answer two main questions, which were already asked by the audience. So thank you very much. One is, can we understand anything about the phase structure at large N? And secondly, I'm going to make comments on these operators, graviton operators in the Engels theory. Okay. All right. So so this was also from some seminar I took, and the convention changes slightly. I'm just going to give a very, very brief recap. So the index now, the R charge I'm going to call Q. Okay, so this is the index that we discussed in all these lectures, raised minus 1 to the F, e to 2 pi I tau times 2J plus Q. And it's quantized like so with N over 3 here. I'll run through this because we've seen this many times. So that's the index. There is a black hole carrying the same charges. These are the gravitational charges in units of N squared. And the simplest black hole has J1 equals J2 equals J. And there's this relation which they obey, which is some nonlinear relation. And the entropy in terms of these charges is N squared times Q squared minus J with some coefficients. And you can write this after solving this relation as one function, which I'm going to call small s. And it's convenient to scale out the N square and write it as a function of s of the gravitational charge N over N square, which I call nu. Okay. And our job is to compare d of n versus s of n over n squared times this. Okay, so, and this also we covered. What's the meaning of the growth of states? The question is there an asymptotic agreement? Actually, when you divide by 1 over n squared, you can even write this as a limit instead of asymptotics, like I was doing in the lectures. Okay, so now both of these are finite quantities, and you can ask if there's a limit. And there are, and here, so S of n, S of nu, we also said what it is in I think the first lecture. At large nu, it scales as nu to the 2/3. You see that. So here I've plotted the black hole entropy. This is the entropy versus the charge for very large values of charges for different values of the rank. Okay, and you see two things. One is you see this growth with respect to nu to the 2/3. Okay, it's a mild growth like this. And then you see the N square growth in this direction. Okay. For reference, I've shown the entropy of a gas of gravitons with the same charges, and you see that it's very, very small. If you actually take, this is the entropy itself. If you divide this by N square and take a limit, then this just goes to 0, and all of these converge to one curve. Okay. And then there are these two limits, large N limit and Cardiac limit. And I'm going fast because we've done all this. Then you can change ensemble to go from microcanonical to canonical. And the questions, so there's this on-shell action which we derived, and the question is this log of the index, is that asymptotically equal to this gravitational action? And again, there are two limits. Tau goes to 0 at finite fixed n, or n goes to infinity at fixed tau. Okay, so all this was a very, very brief. Okay, so now we want to focus on this large N limit. Okay. Oh, sorry, so there's one question, one thing there, oops, which Abhiram asked me about 2 times, and I asked him not now. Notice already now that we already saw that this is true, at least as tau goes to 0. And that should immediately tell you if you've played with modular forms even a little bit, that this function is not a modular form of SL2Z in the normal sense. Okay, it's not any, in fact, it's not. Okay, in any sense, it's not. And that's because, remember, the modular forms, as tau goes to 0, have the behavior in the exponent. So log of the function goes as 1 over tau. Okay? Here we have 1 over tau squared. It's a small detail. It's a very important detail. This cannot be an SL2Z modular form. Okay, so now let's, in order to look at the larger limit, we should consider, let's consider this other representation as an integral over U1 matrices. Okay. So this also we derived yesterday, and you have this. So it's like any matrix model. It's a unitary matrix model, okay, whose action is an infinite number of terms, okay, all of which is governed by one function, which is this single particle index that we calculated yesterday. So here, remember, there are two pieces to this. Oops. This piece, this divided by that, that's the chiral multiplet. There's a 3, and this comes from the vector multiplet. Okay, this we already did yesterday. Okay, so now remember that, how do we solve unitary matrix models? Okay, how do we solve matrix models? The first thing is, so again, I said this is a hard problem, but of course we do have one sort of classic method to solve such large n problems, namely the large n method of Bresait, Six, and Parisi-Joubert and followers. So the first thing you do is you take this measure and you write it as a measure over eigenvalues, flat measure over eigenvalues. This we already did yesterday. And when you do that, you get this van der Monde type determinant. Okay, that van der Monde determinant, remember, is always a two-particle interaction. Okay, so that can also go into the action. And in fact, yesterday I already showed you that that somehow naturally combines with the vector multiplet to give you nice functions. Okay, so at the end of the day, what you get here in our situation, sorry, I should say something, that those of you who know matrix models immediately should say that there's something very funny about this matrix model, namely that every term in this infinite term has a trace U dagger. So there's double traces, which means if you write in terms of eigenvalues, there's a two-particle interaction. Okay, what Bresait, Six, and Parisi-Joubert teach you is that you have an action which you have some one-particle potential, okay, with some minimum typically, and then a two-particle interaction coming from either from the measure or from potential itself. And the two-particle interactions are always suppressed by 1 over n. So the way they tell you how to solve it is you look at the single particle potential, you put all the eigenvalues at the bottom of that potential, and then the 1 over n effect of the two particle, what it does is to make that point into a branch cut in the complex plane. And that's your ansatz, and that's how you have to solve it. Okay. Here, there is no single particle potential. It's all two particles, so both from the measure as well as from the original action. Okay, so that's what makes this a little bit interesting, okay, and difficult. So you write this action as a sum over all pairs of eigenvalues with some potential V. Okay, that potential summarizes that and that. Okay, so I just say that there's one more funny thing about, so that's this I already said, there's a two-particle interaction. There's one more funny thing, namely that, I don't know how to get rid of this, yeah. Namely that the coupling constant here, which is essentially tau, is complex. Okay, and this we spent many minutes on this. I don't want to belabor the point. By now we all know that the tau must be complex, but that's also funny if you think about it in terms of, let's say, the Gross-Witten-Wadia type of models. Okay, the usual story that we understand there is that there's one real parameter like the temperature, and there are two phases, and then there's some phase transition of whatever order, okay, third order in this case. Okay, now here, when there's complex couplings, the story will change. So these are the two new things compared to the usual matrix models. Okay, any questions about this? Okay, so what I'm going to show you next is some work with Alejandro Cabo Bisset, where, so I think it's fair to say that this matrix model hasn't been solved completely. What we did in the paper is to write down an ansatz, which has very interesting properties, okay, which seems very close to the physics. So remember again that in almost all matrix models, except maybe just the pure Gaussian Hermitian matrix model, we don't know how to rigorously solve it. We always make an ansatz and then go with that solution and then see if that agrees with the physics. Okay, very few matrix models, we have a really top-down approach, like mathematically rigorous approach. Okay, there are examples, of course. Alba is one of the experts. But generally speaking, this is how it should go. So that's what we did. And the idea is that because the coupling is complex, the saddles will also be naturally complex. Think about this as some field theory or quantum mechanics, right? Think about the Airy function if you want. If you start with some real integral, make the coupling constant, it's only natural that the saddles also move in the complex plane. You have to think of everything in an analytic way. Okay, so that was our answer, that you allow for complex saddle points. What do complex saddle points mean? So remember these parameters U, these holonomies U, in the original unitary matrix model, that went from 0 to 1, so that the eigenvalues of the unitary matrix live on this circle. Complex means that U becomes complex. U gets an imaginary value. That means that you move away from this original unitary point to something like that. Okay, and in this, there's a natural point in this complex plane, which is tau. Okay, this we saw already. And the story that we found is that the torus, which is defined by 1 and tau, plays an important role. You can think of this as that circle, this is that circle, and then this is also a circle. You make an identification. Okay, there's a natural torus appearing in this game. I'll tell you. A torus or a lattice, which is the same thing, which gives a family of saddles labeled by these lattice points. For every lattice point, you get a saddle point, large n saddle point of the matrix integral. Okay, with some condition that and this is to avoid overcounting. And these saddle points in general have macroscopic entropy. So the 0, 1 point is identified with pure AdS, and the 1, 0 is identified with the AdS black hole that has order n square entropy and exactly the entropy of the black hole, the on-shell action of the black hole. Okay. That's what I'm going to tell you next. So any questions about the idea? Okay. So we start with the lemma. So suppose you have a matrix integral of the sort that I showed you, meaning that there's an action which is a pure sum of two particle interactions, which is even. This can be also relaxed, and periodic with some period t, which can be complex. And you want to solve the saddle point equations. Saddle point equations are here not appearing because of the coupling constant going somewhere, but because n itself, the rank itself, goes to infinity. That's the large parameter. So the lemma is that if there's a period of the potential t, then the uniform distribution between 0 and t is a saddle point. Okay, it's a very easy thing to show. I'll leave this as an exercise. It's a 2 to 3 line calculation. Okay, so uniform distribution, we know, everyone knows what that means. So remember, in these matrix models, the goal, what we want to calculate is the distribution of eigenvalues. You want some distribution of eigenvalues which solves the saddle point equations. Okay. So if it's periodic, you just put it on that circle. And then the second part of the lemma is that the action of this distribution, uniform distribution, is just the average value of the potential along that period. This is also not very difficult to show. It's 3 or 4 lines. Okay. Right. So now if you want to apply this, this kind of lemma, you need to show that you have some complex saddle points, you have some original contour of integration, you want to show that the contour can be deformed to pass through the saddle points. And then eventually what you want to do is to have some exact contour which calculates the integral. That's always a very difficult problem that we're not going to do at all. But you want to show that the contour can be deformed. Usually that comes for free because your deformations, people have talked about deformation, complex deformations of matrix model. So usually these deformations are complex analytic, they're holomorphic or meromorphic. What we will do, it's not the case. And therefore we need a separate argument, and we give a separate argument in the paper. I can do this separately. It's a bit technical, but I can tell you why that's the case, which holds so far, as far as we understand, so far we've only managed to do it at infinite n. Okay. But at infinite n, it works fine. Okay. So what is our deformation? So let me now guide you through this. So the original model is like that. Remember, there were these elliptic gamma functions in the game. So I've already made the shift of 1. That's hardly our problem now. Now let's look at these elliptic gamma functions a little better. Okay, they are, as I said, people in the math literature have considered this, but only relatively recently, compared to, for instance, theta functions, which have been studied, by the greats for more than 100 years. Now, here is some property that we will need. This elliptic gamma function, it's very easy to check. So this part is very easy to check, that there's a periodicity. So we'll only focus on sigma equals tau. So there's a tau variable and there is a z variable. The z variable you should think of as living on a complex plane, and tau is fixing a point, a lattice on that complex plane. Okay, just exactly like in theta functions. Okay, so now you ask, so your sort of complex parameter is z. So there's a periodicity in z goes to z plus 1. That's trivial from this expansion. And when z goes to z plus tau on the other cycle of the torus, or the other leg of the lattice, there is not a periodicity, but there's a quasi-periodicity. In particular, you'll see that gamma of z is related to gamma of z plus tau with a multiplicative factor, which is theta naught inverse, and theta naught is the Jacobi, odd Jacobi theta function divided by eta. Okay, I'll tell you this in a second. Okay, so it's not quasi-periodic, so it's not periodic. And therefore, if you want to use our lemma, which depends on periodic potentials, okay, we cannot use the analytic continuation of the action as it's written, because it's not periodic. Okay, of course you can consider the analytic continuation, no one stops you from it, but there's something in the problem which sort of asks you to look for periodic uniform potentials. That was our intuition. But there's a small problem, namely that these things are not periodic, they're only quasi-periodic. This is exactly like like for Jacobi theta functions. Okay, that the Jacobi theta function, here's the definition. This is I haven't written, but all of you should be able to recognize, if you've taken some basic string theory course, that this is just the odd Jacobi theta function divided by eta. Okay, usually you also have 1 minus q. Okay, maybe times some factor of zeta. So this theta naught, so let's do a warm-up exercise. So the idea is to take this this elliptic gamma function, okay, and somehow deform it to make it periodic, make it doubly periodic. It's almost doubly periodic, but not quite. Okay, so first let's see how to do that for a simpler example. Okay, let's see how to do that with the Jacobi theta function itself. Okay, so take this lattice of 1 and tau. Okay, q is e to the 2 pi tau, zeta is e to the 2 pi z, the standard notation. And any complex point, I'm going to write z1, I'm going to decompose it along the lattice directions 1 and tau. So the Jacobi theta function itself is also quasi-periodic. It's periodic along this, but not periodic along this. Along the tau direction, the lack of periodicity is just a simple phase e to the 2 pi z. Okay, but it's not 1. But you can cure it. How do you cure it? Well, you construct this function called p, okay, which is theta naught times q to the half second Bernoulli polynomial, in Z2. Okay, you break holomorphy, okay, in this. Now, the idea is that theta naught, when Z goes to Z plus, picks up a linear term. So you engineer it. You put a second order polynomial whose difference when you change it is a first order polynomial. So that precisely cancels this. Okay. But not quite precisely. It only cancels the real part. So what remains is a phase. So here's the statement. Firstly, the deformation is such that up to some constant piece, this function p, when z2 equal to 0, is theta naught. Okay, so it's a real deformation. You start with something, you make it something else. You extend it. Okay. Now, the absolute, as I said, p is almost, so p is essentially elliptic except for a phase, which means that the magnitude of p, the absolute value of p, is elliptic. So I'm going to use a notation which is used by some mathematicians, but this is something in undergraduate we taught this is wrong notation. Namely, elliptic functions, of course, should be meromorphic. We're not talking about meromorphic functions, but elliptic, I just mean doubly periodic functions. I'll often interchange these two notations. Okay. So it's elliptic. Okay, so this is all of this so far is just engineering. You just make this, as I said, to make it elliptic. Now there's a third property of the function p, which is that it's a modular function. Okay, that's not obvious if you didn't know this. Remember, theta naught is not a modular function; it's a modular form. But when you do this, this dressing solves two problems at the same time. It solves the elliptic quasi-ellipticity as well as the quasi-modularity, not quasi, as well as the fact that it's not quite modular. And you get that, okay? And you can either prove it by looking at the modular transformations of theta naught and explicit forms of this, or there's a very nice formula which goes back to Chronicle, which gives you an explicit expression. So he says, it's called the Chronicle second limit formula. It says that he gives you a formula for log of p, absolute value p. There's a limit. This is hardly going to bother us. This limit appears because of a certain weight in this, because the weight here is 2. Again, this is fairly standard in the theory of modular forms. It's not, you can essentially think of this as s goes to 1, s equal to 1, except that there's some small convergence issue which doesn't bother us here. Okay, what he tells you is that log of p, absolute value p, can be written as a lattice sum. Okay, as such, you can write it as a double Fourier expansion along the lattice. Okay, whose coefficients are m tau plus 1 n absolute value square. As I said, just take s equal to 1. Okay, so this is like if for let's say you have some, let's say z1 and z2 equal to 0. Okay, then you have essentially just the non-holomorphic Eisenstein series. That's perfectly modular. That's the place where it's not convergent, so take this limit. And here, for other values of z, you have this interplay of the Jacobi and the modular variables. Okay, so I mean, this by the way is Chronicle spent a lot of his life developing such things. I mean, so he picked up from where Eisenstein developed this theory of modular forms. Eisenstein thought of modular forms really as some kind of holomorphic sums. And Chronicle, but then he also had an idea that there should be lattice sums, not as Fourier sums, but lattice sums. And Chronicle picked up on that and made it into non-holomorphic. He studied non-holomorphic forms. There's a very beautiful book by André Weil called Elliptic Functions from Chronicle to according to Chronicle and Eisenstein, and I absolutely recommend that book for everybody. So it's very accessible to us as physicists. Okay. Okay, so that's the trick. Okay, so we're going to use this classical trick, which has been known for theta functions, but this gamma function, as I said, is a relatively new object. Mathematicians haven't studied this much, but exactly the same thing can be done for this gamma function. Okay, we construct this function called Q, which is the following. So you have to dress it up. You have this 1 over gamma times theta naught to the z2 times the third Bernoulli polynomial. Again, you break holomorphicity. And now here are the properties. So firstly, it's an extension, namely when z2 equal to 0, Q equals gamma inverse. Okay, I'm going to extend gamma inverse. The absolute value of Q is elliptic. Okay, so it's periodic in both directions. Okay, so far the thing mirrored what I told you about theta functions. And now the question is there any surprising formula about modularity? Okay. And the answer is there is, but it's not what you expect. It's not modular. Okay. However, the lack of modularity, so if Q transformed like a modular, like a Jacobi form under Z and tau, okay, of weight 1, this right-hand side would be 0, but it's not 0. And instead, it's a function which is a nice function. It's a very beautiful function, which has been studied by number theorists for about 30 years or so. In particular, Bloch and Wigner have studied this. They invented this function. It's often called the Bloch-Wigner elliptic dilogarithm. Okay, many of you have heard this joke before, but I want to say this again because it's not just a joke, that this is neither the Bloch that we know nor the Wigner that we know. They're both number theorists, and they invented it for reasons known to them. I mean, it has to do with, I'm happy to explain as much as I understand later. It has to do with L function values and studying elliptic curves and so on, Hecker theory and so on. Okay, but the fact is they give us this function, and Zagier and Ramakrishnan and then others have studied this function, and that's a very beautiful, simple formula, exactly of the sort of Chronicle, namely it's a lattice sum, okay, with a double Fourier expansion. Okay, and here you see in the denominator an Eisenstein series type of object of weight -1, -2. All right, sorry, 1, 2. Okay. Okay, so if all of that sort of didn't make too much sense, the thing you can take out of this is the fact that from this formula and from this expansion, you can just work out what is the Fourier expansion of log Q itself. Although it's not a modular form, okay, the fact I think I can write on this. Yeah, here. Okay, notice that tau, I've never done this before, so I'm trying. There you go. Tau equals tau1 plus tau2. These are absolute values, so this is real. So I'll go back to this. This is real, and that's real. And therefore, the imaginary part of this equation only comes from this. Okay, so you just take the imaginary part of this, and that gives you Fourier expansion for log absolute value Q. Okay, that's what is useful for us. Okay, then there is this other question of whether this means something and so on, and you can ask me again after the talk, but I hope at least I answered some of the questions. So there is some modular property. The name for such modular property is called, so these are called period functions for reasons that if you don't know, then I can't explain in 2 minutes. If you know, then you already know. Okay, it's a nice discussion later. Okay, great. So as far as we're concerned, we get a Fourier expansion. So let's hurry up. Okay. So, so now we can extend the action to a doubly periodic function. Okay, so it does not, at the old contour, it doesn't change. But now we can apply our lemma just directly because you have periodicity. So you have a family of saddles labeled by any lattice point. And the action of the saddle, which is the average value of the potential along that cycle according to my lemma, the one we wrote with Alejandro, all of this is explained in my paper with Alejandro in 1909, September. The calculating the action is easy because the Bloch-Wigner formula, just gives you a Fourier series. So the average value is just like, you just have to do one integral. Okay, just have to read off something. And here's the answer. The action along the saddle point labeled by M over N looks like this. It's a cubic divided by quadratic. Here, there is a Dirichlet character, which is 0, 1, or -1, depending on whether you're mod 3. This is for n equal to 4 super n. The 3 comes for the same reason that we've seen. Okay, the 0, 1, this is for m not equal to 0, the 0, 1 action is 0. Okay, in particular, the 1, 0, if you plug it in, you get this action, which we've now, I hope all of you sort of will remember this action in your dreams. It's exactly the supergravity action of the black hole. Okay, 2 tau plus 1 cube divided by tau square. Okay, so what we've managed to do is to recover the black hole as a large n saddle point of the matrix integral. Okay, so now you can ask, I have all these phases. Can I draw a phase diagram? Okay, you can do that. You can just compare the real values of these actions against each other. And yeah, so again, notice there's a tau square. So by the way, I should have said one thing technically, which is that the 1 over tau square appears. So this side is a modular form. Okay, so 1 over tau, but there's a tau here already, and that's what is giving you the 1 over tau square. Okay, there we go. So let's now draw the phase diagram. So first, let's go near tau equal to 0. So firstly, notice that there is a symmetry in this problem, which is the parity symmetry that I discussed earlier. Maybe I draw it like that. Okay, I have I've shifted the origin such that this should be really sort of the origin, that is 0. Okay, this is some other units we used in the paper. This is your black hole. Okay, and this is this other the parity mirror of the black hole that I discussed at the end of the last. So this lives, if you want, at e to the 2 pi over 3, and this is e to the minus 2 pi over 3. Okay, and you can see that they both have the same actions. So in this formalism, it comes as 1, 0, and 1, 1. And you see that as we start going towards tau 2 equal to 0, let's just focus on one of them, because everything is a mirror. As you start going towards tau 2 equal to 0, you see that this dominates. When tau 2 is large, the AdS dominates. When tau 2 goes to 0, the black hole starts to dominate. This is according to our intuition coming from physics, that at high temperature, there should be a black hole, except there's not a temperature. Tau now plays this role of some complex, of some supersymmetric parameter. Okay? Right. Now what happens when you go further, and here is the fun part, that you get infinitely many more saddles. At every value of mn, you get a saddle point. Okay? And around that point, you get that it's that which dominates, and that you can see because of this. Whenever tau goes to minus n over m, this blows up. Okay, so for the black hole itself, its tau goes to 0, but as you go close to any rational point, it's guaranteed that you get a new phase. Okay, and this was in the paper. Then I should say that this some small, again, technical issues, but important, that this, so one of these phases, the ones at tau goes to infinity, has to be treated carefully. And in fact, this expansion sometimes gives you have to be worried about convergence and so on. And if you do all that correctly, basically you get the black hole action. This changes a little bit. You get the black hole action exactly where you expect it from supergravity. We already derived the action. And so if you, for instance, if you just compare the black hole phase with the pure AdS phase, by construction, I mean, not construction, by our solution, if you only compare those two, that's precisely the Hawking phase transition in this supersymmetric story. Okay, but now there are all these new saddles. Good. Let me make some comments. So now we have a lot of saddle points. So now you can write the index as a sum over these saddle points with this action that I showed you. Okay. Now let me try to make sense of this formula. So firstly, this formula is not, it's not a mathematical formula, for the same reason that in physics, it's very difficult to write equalities in this kind of game. You're doing saddle point approximation, and the meaning of this formula is that there's a lot of saddle points, and around each saddle point, we have a perturbative expansion. What we managed to do by this method is around each saddle point, we get the complete perturbative expansion. It's not that you get a convergent formula here, unlike for modular forms, okay? But you identify an infinite number of saddle points, and around each saddle point, you get the complete action, okay? There's some nice comments in a paper that Alejandro wrote last December, a couple of months ago, about the exact formula. Okay. Then I should say that there is something like this has happened before in physics, namely when we were studying AdS3 CFT2, that the CFT2 elliptic genus is also written, can be written naturally. In that case, as a convergent expansion, as a sum over saddle points. Also, those are also lattice points. Those are, you can also think of them as Mn with GCD equal to 1. Okay. And there is a gravitational interpretation namely that the gravitational solutions are essentially just orbifolds of pure radius 3. So the BTZ is one of them. It's the orbifold of pure radius 3, but there's an infinite number of orbifolds which were identified here. Okay, so the natural guess is that exactly the same thing happens here. We have to be a little careful because in this case, the AdS5 and AdS holes are not, they're not orbifolds of one another, okay, unlike in AdS3. Okay, AdS5 black hole is even locally looks different. The curvature looks different. Okay. Now, if you look at this action of this MN phase, then you see that you can also do the microcanonical. You can ask what is the entropy contained in that action, and you'll see that after some change of variables, essentially there's a 1/n, both in the action as well as in the entropy. So sometimes people call this partially deconfined phases. So the AdS is completely confined. The black hole is, you have an n square, and these have n square over m worth of entropy. Another thing is that our analysis just gives you new Cardi-like limits. So this is something I was stressing, and this is the question that was asked, namely, are there other limits on this circle? And I said, please hold on, and here is the answer. So from this analysis, it's clear that every rational point in tau, namely q equals e to the 2 pi I times a rational point, there is a singular behavior, and the entropy goes as 1/m. Okay, that's your answer. It's a very explicit, clear answer. And you can study now the Cardi-like limit. In each case, the imaginary part of tau goes to 0, but the real part goes to a rational number.
Can I ask one question here?
Yes, please.
So if I understand correctly, like in this analysis, all the subtle points have like a uniform distribution of the eigenvalues, right?
Yeah, along this complex direction, that's right.
Right. Normally, like if you have a uniform distribution of eigenvalue, that's associated with confined phase, and in the deconfined phase, there is some support. So, but here, like it seems the interpretation, like the relation between like distribution and phase seemed a bit tricky.
Yes, I completely agree with everything that you said. In fact, I should have said this long ago. So when I was first introducing the matrix model, so before going into the complex plane, the only distribution, the only solution to the real matrix model that you can think about is really the uniform distribution along 0, 1. And this is the one which was used in these old papers, and you can check that the entropy is 0. Yeah. So now you can ask, so there are two possible ways. You can either say, well, let's try to study complex saddles, okay? But then try to make sense of the eigenvalue density, or at least the real parts or something like this. Okay? So that we didn't manage to do this. Okay, there's some very interesting clues which I don't want to discuss here, but I'm happy to speak to you privately. Okay, about how that's going on. But we didn't want to do it. But instead we said, look, the solution, there's an obvious solution, namely that it's a uniform. So what I'm saying is, if you try to do an analytic extension, the meromorphic extension, you do not expect uniform distribution for these other black hole phases. That's exactly what you just said. Nobody has solved this problem yet, but there are some interesting clues. Our intuition in this paper is that the intuition that the uniform distribution must be a solution is true even for complex saddles. So let's explore it. And what we found is that the whole physics just dropped out of it. Okay, it just came out of that very naturally. And roughly speaking, I can give you a hint about where I'm going with that. It's that I should say one more thing. There was another motivation to do this whole thing, namely that there is another way to treat the whole integral, as many of you know, which is a very beautiful piece of work by Benini and Milan, which they don't ask this question of saddle points. Okay, they said, we don't want to find saddle points, but instead we just want to solve the integral, use some contour deformations, and what they find is they pick up some residues, and again, they also can't identify all the residues, but they can, in their papers, they identified one which looks like AdS5 and one which looks like the black hole. Okay? The black hole one had precisely this uniform distribution in the complex point. Okay, so one question we asked ourselves is that a saddle point in some sense? Okay, so that's one thing we answered. So it's a saddle point in the sense that I explained, and then later the story went that all the saddle points that we found, that you could also sort of, you could already see that from this beta and such type of point of view. And then we could calculate the actions very easily. Then you could also calculate the actions. Eventually, people calculate the actions also in that framework, and it all agrees. So there's a one-to-one mapping. But there's also this more physical understanding which we're after, which we still haven't got, namely, is there really a saddle point? And my guess is that the labels and the action that we find should continue to hold, and at least in the tau goes to 0 limit, this can be checked. Okay, when you have tau goes to 0, you can ask, can I find some saddle point, real saddle point in the sense that people used to do it earlier? And this you can use these asymptotic expansions that I gave you. Okay, you can extend that asymptotic expansion. It's a nice paper recently by Liu, Lescano, Pandosayas and somebody else, I'm forgetting, maybe Junho Hong, who actually do that. They solve these saddle points in that limit, and there's an explicit match with this action. Okay, so this cubic action seems to agree even in that saddle point, and I think there's more to be said there. Okay, so I don't want to say more now, but ask me again if you want.
All right, thanks.
Okay? I hope I gave you some idea of what I understand.
Yeah. Yes. Thanks.
Okay. So that's that. Cardi-like limits. Very good. I want to skip this very briefly. This technology that we developed also helps to do the Cardi-like expansion almost in one line. Once you understand the main deformation, the elliptic properties, the properties of this function, the Fourier expansion of this function immediately gives you these B2, B3 functions, and you can see in the Cardi-like limit, you can just write this down in 2 lines. Okay, so that's another advantage of this approach. Okay, so now I want to, so when did I start, Alba?
Yeah, I think you can take it like maybe 5-10 minutes.
10 minutes? I started at 10 past, right?
Yeah, more or less.
Yeah, okay, so then let me tell you about the other question that was asked. Where was I? Here we go. Okay, let me first give you a context. So this is a slight change in subject. So those were saddle points, and now we want to ask about operators. So what we studied, so let's back up. So stick to n equal to 4 super Young mills. We want to study states or operators with these charges, J1, J2, R. And for n equal to 1 super Young mills, R is actually embedded in SO6 or SU4. So there's R1, R2, R3. This I explained in the first lecture. Now let's study, so in the black hole, so we studied 2 limits. One was the Cardi limit where you fix large n, so fix the rank, take charges to infinity. The other one is the black hole where the gravitational charges are fixed. So both the charges and the rank scale to infinity. Now I'm going to introduce a third limit, which is you just fix the charges, okay, and then take n to infinity. Okay, maybe this is what Sasha was asking about. Okay, you just fix the charges, not the gravitational charges, the field theory charges, and take the rank to infinity. So in this horizontal vertical idea that I was giving you, you just go vertically. Okay, this I will call the n equals infinity limit for obvious reasons. Okay. In this limit, what is going on? In this limit, it's clear that you're studying small fluctuations around AdS 5. Okay, because you have some very small energy. In gravitational units, the energy goes to 0 and the thing becomes weakly curved. So in other words, you're studying a gas of gravitons and all its superpartners. This problem was solved by Gunaydin and Marcus in 85, because essentially it's a problem of representation theory. You have to take the supergroup and you ask, what are all the fluctuations? Okay, they did this. And there's some group theory. You look at some R symmetry. So they did this for n equal to 4, and then people extended it. So you look at the R symmetry group, SO6 algebra, and you have to look at some N00 representation of that. And the graviton multiplet is n equal to 2. These are all details I'm going to skip. The point is that the Hilbert space of these small fluctuations in this limit is known. It's been known for many years. Now you can ask, let's calculate this single graviton index, the one that I discussed yesterday, on this Hilbert space. Okay, so it's exactly what I said. It's trace minus 1 to the f, the single graviton Hilbert space, which I just talked about, times x to the 2j plus r. I've changed variables. I've made x cube equals q, what used to be q, because this is how it was in my paper. And you can do this for, you can also study like more general partition functions. Okay, they may or may not be protected, and let's stick to this index. Okay, you can study this in as much detail. You know the whole Hilbert space. Okay, you write this index and you find this. Okay, 3x squared over that. Okay, you find this. Now, you can ask, what is the multi-particle formula? What is, sorry, this should be Q, of course. What is the graviton index, okay, on this Hilbert space? Okay, and the answer is given by exactly the same platistic exponential that I showed you yesterday. Okay, you do this, you know this explicitly, you plug this in, and what you find is this infinite product. Okay, so if you sort of observe this exponentiation, you'll immediately see why that becomes this. Okay, there's a 3 and a 2, which is this 3 and a 2. Okay, and similarly in the denominator from the minus sign. Okay, and these are just some eta quotients. Okay, and now you can ask, what is the growth of states of these gravitons? And you find this again is basically is just an eta function. So it goes as some square root of n, where n is the charge. Okay? And note that there is no dependence on the rank. And that's because you've scaled the rank away to infinity. It could have happened that you got something infinite, but you didn't, because AdS space makes sense. And so this is the graviton growth that I showed you. It's very, very small because there's no n square here. For the black hole, there's an n square, and there's no n square here. Now, on the Yang-Mills side, you can ask for the same, you can try to answer the same question. You can ask, what are the operators which represent these states in the Yang-Mills state? So let's first do n equal to infinity. Okay? So at n equal to infinity, there are no trace relations because the matrix is infinitely large. Okay? When n is finite, there is the Cayley-Hamilton theorem, but n equal to infinity, ignore it. Therefore, so single trace operators are single particle states in, so single trace in CFT is single particle in AdS. That's sort of AdS CFT, the first chapter, or the second chapter. And because there are no trace relations, you can say that the multi-trace is in one-to-one correspondence with multi-particles. Okay, so there's no subtlety here. And this this study was performed by, in a very nice paper by Chang and Yin, and they confirmed this explicitly by constructing these operators dual to the single gravitons. All right. So this essentially they had to study the representation theory of the supergroup in the field theory. And they have some very nice method to do this, and they got a one-to-one map like so. Okay. So that's the history, and now I want to come back to that. Okay. So this is what Chang and Yin studied. Okay, and they sharpened the statement in the sense that I just said. There was also earlier work, which is very nice, by Yannick. Oh, I don't know why I said this even. Yannick and Tsetselevsky and Grant Grassi, Kim and Minwala, and Chang and Yin sort of solidifies this very well. And then in their paper, they conjecture that, so at infinite n, you see that the multi-trace BPS operators are in one-to-one correspondence with multi-gravitons. And what they conjecture is that they asked, how can this statement break down? It can break down if there are relations, okay, the relations between the matrices at finite n, trace relations, or if there are sort of new states appearing. Okay, one of them will kill the index, and the other one will give more states. Okay, and based on some calculations for the first few orders, they conjecture that in fact this does not happen at finite n. They said no new operators or relations appear at finite n. Okay? Now this seems to be in contrast and contradiction with what we just said. Right? Here is the graviton growth of states. Those are the black holes, which we have now checked from 3 different points of view, 2 different analytic methods, and also on the computer. Okay, and clearly this is much bigger than the graviton. Here's square root of n versus this large n growth. Okay, so what is going on? What are these operators? Are they black holes or gravitons? Okay, now the answer, I think the best answer is that they're both. Okay, I think this is the right answer, and I'll tell you this is consistent with everything we know, and there's more to understand here. Let me say in what sense do I mean that it's consistent with everything we know? Now, at large, so we have two checks. At large values of charge and large values of n, we've already done the calculations analytically. So we know it agrees with a black hole. So there must be so many operators. We don't know which operators there are. Okay, that's still open. But the question is it true that it's the same matrix integral that gives you the small charge gravitons that Chang and Yin studied? Okay, Chang and Yin didn't quite study that. They did what I said, namely, you just take the graviton operators and then use the Platistic exponential on them. Okay, there is no gauge, there's no discussion of gauge invariance in that. Okay, they just sort of first looked at gauge singlets and then did the multi-particle sum. Okay, so the question is that the right thing to do, or not? And the answer is it's certainly correct, and that's what I want to show you. Okay, so what I want to show you is that from our formula, which is just the index which the field theory tells you to calculate, you get also the gravitons. Okay, just like you get the high energy black hole growth of states, as I showed you, you also get gravitons. So here's a table. This is for finite rank. So dn, so n is the rank. So this is n equals 2, 3, 4, etc. And this is un. In my first lecture, before I started anything, someone said, is it important un versus sun? In this table, it's going to be important. Okay. This is un, and I compare this with this graviton, multi-graviton index that I just showed you, okay, in my handwriting. And what you see is something quite remarkable. You see that for low values of charge, so again, to repeat, this is the field theory index at finite values of rank, and this is the multi-graviton index. At low values of charge, the field theory index completely agrees with the graviton index. Okay, then it begins to start to differ. Okay, starts to differ, etc. Okay, and now let's see this as a plot. So here, these are the field theory quantities, which I already showed you, but I showed you at a very, very large. Okay, here I'm showing you sort of the smaller part. So this thing will become the black hole, like I already convinced you about. Okay, this one is the multi-graviton index. And you see what is happening. At very, very small values, you don't even see this on the graph, you should look at the table. Okay, at very, very small values, all of these field theory curves agrees with the multi-graviton. You almost don't see it, it's somewhere here. Okay. Then the field theory values actually dip, they go below the graviton. And then at some point there's a crossing, and then it climbs up, and then it climbs up a lot, and this one goes, so this is square root of n, and this is large n to the 2/3, small n to the 2/3. Okay, that's the behavior. So what I want to say is that we already found this part analytically, and now I'm going to say that this part, this observation, you can also explain analytically. Okay, this is the third observation in these graphs that I showed, that before the oscillations take over, there's a little bit funny happening. That's what I want to explain now. Okay, this is my last slide. Oh, sorry, but in order to say this, I have to say one thing. So firstly, there's a small observation, namely this multi-graviton index. Okay, there's a small sort of coincidence which you can observe, which was already observed in the original papers, but I think it was misinterpreted. If you write this single trace operators, which I actually showed you how to calculate, okay, you find that that is precisely equal to 1 minus this, 1 minus this object, okay? And therefore the multi-graviton index, which, I don't know if I showed you a formula, here it is, okay? If you see this formula, I'm going a little fast, but you can work this out yourself. The multi-graviton index essentially can be written like this. It's a product of n equal to 1 to infinity of 1 over 1 minus single particle of x to the n. Okay, that's just an observation so far. And now what I want to show you is how to sort of reproduce that observation. So start with this, our field theory index, the thing we've been studying to death in the last 3 days, about which now you're going to have dreams, I hope, all of you, and not nightmares. you write this as this matrix integral, UN matrix integral, and now you do the following. You keep finite n, you take this exponential and expand it. It's an exponential of sums of trace U daggers, expand it. What are you going to get? You're going to get some sum, infinite sum, and in fact, if you think about it, you'll just get a sum over all partitions because there's an infinite number of things here in the exponential. So you can just keep having trace of U to the K1, trace of U to the K2, trace of U dagger to the K3, etc., etc. You'll have operators of this type. You'll have operators of strings of traces to some powers. Okay, and those are labeled by partitions. That's all I've said here. Okay. So I hope that's clear. Let me, if not, just take it from me that take the basic formula, expand it, you'll get some traces. Okay. Those traces, there is a classic formula due to Frobenius, who says that any such traces can be expanded as a sum of characters of UN. Okay, given such a partition of integers, recall, I mean, this is the famous accident, which is that the characters of the unitary group and the character of the symmetric group are both labeled by partitions of integers. Okay, it's really an accident. It happens to be the case. You can think of this as I mean, not an accident. It's a beautiful observation. You can, from Young diagrams, you can see this. Okay? I think all of you know this. Okay, and this is the formula. It says that any such operator can be written as a sum over characters, chi tilde the character of the UN group times a character of the symmetric group labeled by the partitions. Okay, with the constraint that that partition should be part of the UN representation theory, which means the Young diagram should have less than n rows. Okay, that means that the length of the partition should be less than or equal to n. Okay, that's the Frobenius formula. So expand the exponential, use the Frobenius formula, and you get the index as a sum over partitions with some object which has to do with the single particle index with some combinatorics times a sum. Times. So remember, there was an integral over du, and then now you have integral of character times a character conjugate, and that's the standard sort of orthogonality relation of characters, which says that that's either equal to 1 if the two characters are the same, or it's 0 otherwise. Okay, you use that, and therefore now the unitary matrix you completely remove from this game. You write the formula completely as a sum over partitions. Okay, sum over random partitions, all partitions with some weight here, and the weight is this interesting thing. It's a sum. It's a square of characters of the symmetric group with this constraint. That's very important. Okay, and it's this constraint that's giving you the growth. You take this because of this double scaling that we're doing. If, on the other hand, if you take n equal to infinity, then this constraint that the length of the partition is less than or equal to infinity is no constraint. You sum over all partitions. Okay, when you sum over all partitions, you use the second orthogonality relation for characters of the symmetric group, which says that this is equal to 1. Okay, and therefore you just get a sum over partitions of this function, and that using some simple combinatorics, you can see is exactly equal to 1 over 1 minus is. Okay, so this is the relation between n equal to infinity and the single particle trace, but we already, as I just showed you, there's a coincidence that that is exactly equal to the multi-graviton trace. Okay, so you can really analytically understand this, so how things are changing. Okay, this finishes my comments, and this finishes everything I have to say. Maybe I just end with some questions here. These are things which I think are worth looking into, many things worth looking into. Thank you very much for all the attention for the last 3 days and all the questions.
Yeah, and thank you very much for the beautiful set of lectures. So, are there any questions? If not, maybe I can start by asking one. So if on the field theory side, is there any concrete attempt to go beyond the n square, subleading correction analytically?
Yeah, so in the Cardi-like limit, you can do that.
Yeah, of course, in the Cardi-like limit, but I want not Cardi. In the Cardi, I know you can do everything, but that's like a very special corner. What about the full index? Can
not that I know of, but yeah.
But do you think this modularity structure may give some hints?
Yes. So that's exactly. So thank you for it. So that's it. So remember that the whole story that I discussed, this extension holds at finite n. We used it at n equal infinity. It holds at finite n, and there are things there which still haven't been used. There's a lot of power in those things which can be used. Yeah. So I think that's one way to analyze this problem.
Thank you. So
I should also say that there's this. Yeah, so there's this Cardi-like limit. You can try to extend the Cardi-like limit and get some full asymptotic expansion. That you can do at finite n. People recently have looked at log n corrections in that kind of a limit. This is the same paper I mentioned, Liu, Pandusayas, Hong, and sorry, I might be mixing the authors, but it's that gang, and Lescano, and maybe Arash.
Yeah, but in that paper, it's either, I mean, if I don't want Cardi, I want the full matrix model. Yeah. They can only do that numerically, right?
That's correct.
That's okay.
Yeah, but in the tau goes to 0, they have a complete asymptotic expansion.
Yeah, no, of course, the Cardi limit, I totally agree.
Yeah. No, I want to emphasize that because oftentimes people think of Cardi limit as just the leading singularity, but you can also have subleading terms and up to exponentially subleading terms.
Thank you. Are there any other questions?
Sorry, can you comment on, you have a couple of points here on the last slide which you didn't have time to discuss.
Yeah.
What do you have in mind? Or?
Okay, so this one I kind of discussed. What are they in gravity? So the sort of obvious words to use is that they're orbifolds, right? Just either based on the AdS 3 intuition or the fact that the entropy is 1 over n. Okay, there must be some kind of 1 over m orbifold, and this I think has been or will be clarified in some upcoming paper. I've heard some talks by Aharoni, Benini, and maybe Milan, and maybe someone else. Okay, so there's some work in that direction coming up. So the interpretation in gravity, that will be very nice. So this is our prediction from the matrix model that Alejandro and I did, and it will be very nice to see the explicit gravitational solutions. This I mentioned a little bit that, okay, so there is this torus coming up. Yeah, so we've seen a torus appearing in the background in many interesting problems like Seiberg-Witten theory. Okay, and each time it's led to some really powerful, so it's turned out to be very powerful. So that was just a sort of remark of that sort, that maybe it will be. I don't have explicit comments here. Role of modular symmetry, this is going along the lines of one of the things, so very useful things you can do is exactly what Alba was suggesting. I'm more interested, I mean, that's interesting certainly. At a formal level, there's also this issue of what kind of functions these are and why these functions are appearing. I mean, for instance, for AdS 3 strings, so for AdS 3, for the usual flat space black holes, we think of these black holes as some kind of wrapped string, right? Some D1, D5 string or something like that. And so that explains the modularity. Okay? Here, sort of experimentally, we're discovering that it's not quite modular, these period functions, and there's this whole mathematical machinery behind it. Can we understand this? Why is this appearing from the physics? I mean, that's our real interest. Okay, so the fact that we know exactly what the symmetry properties are, that might be useful. This is, I think, a very nice exercise which should be done. This is doable by, I think, advanced student or a postdoc. That we have this deformation of the action, and as I said, it clearly reproduces all the answers. In large n, we have some understanding, but it looks like it has a finite n role as well. And it really suggests that this deformation should be understood in physics as a Q-exact term. So the answers are remaining the same, but maybe the form of the distribution is changing or something like this, right? Okay, so that's what I meant. And yeah, so this is my prediction that you should be able to write the whole thing as a Q-exact deformation of the super-Young's theory. This is very close to my heart. This last thing that I said, which I've, sorry, Sasha, do you mind sort of switching on your video?
Yes.
It's very disconcerting to speak to a screen. Yeah, this thing is really close to my heart. This last thing that I said, that the whole Young-Mills theory, which has been emphasized that it's some matrix integral. There's another way to write it, which is there's no matrix at all, but instead you have a sum over random partitions. Okay, and now there's this whole sort of whole Russian school of like really reams of work on random partitions and how you can think of saddle points in such models and so on. I shouldn't say only Russian. This in physics, this has been used very, very fruitfully by Gross and Taylor, okay, for 2D gauge theory. That's what I meant here. In fact, that's the only thing I knew, and then I discovered the mathematical work later. And that will be fantastic. I think if you have some picture of some sort of young tableau and what these saddles are as some sum over random partitions, that will give a very physical meaning to all of this. And these ideas of Gross-Taylor, I think, are the right ideas. Okay, except that the problem here is much more sophisticated. It's just an infinite number of terms and so on. Okay. This I don't want to say too much in this audience, but I mean the fact that, but this is also very interesting. I've been talking to mathematicians. The fact that the particular functions that appear, I always like to take them seriously. And the reason these functions appear is because, so usually in physics we never worry about this. In all these modular forms, what we always want is the coefficients of the modular forms. But in mathematics, modular forms have two roles. One is the coefficients. Okay, that's by now so well known. It's permeated the physics literature. But there's another very, very deep and important role of modular forms, namely the value of the modular form at a particular point in the upper half plane. Okay, this is not so well known by physicists. And those values are all number theorists get excited by those things. Those are the things that appear in these conjectures of Birch, Schmidt, and Dyer, and so on. Okay, and again, it's a miracle. People don't know why it's that, but those transcendental, sometimes algebraic values are captured by the values of modular forms. These are called L function value. I don't mean values of modular forms. They're somehow related to modular forms. So typically the way it appears, you take a modular form, you write its L function, and then take a value of the L function, okay, or some Hecke character or something like this. And these functions that appear here have come up in these kind of discussions in the maths literature. And yeah, I mean, if those things have some physical manifestation in Supergravity theory, I think many people will be very excited about this. So that was this.
Thank you.
Are there any other questions?
Can I ask yet another one? So is there some like a generalization of this index in which you have some like a supersymmetric Wilson loop inserted? Well, this is a question related to like a partial deconfinement, whether we can see it more physically.
Yeah, so I think there should be something like this. So it's something I think on and off about, and I'm happy to discuss this with you. So
okay. Yeah,
I think we should be able to find some observables of that form whose answer is given by these phases. I don't know the answer.
I see. Thanks.
One way to answer that question would be to use the symmetry properties. Right? You try to sort of make an observable which has the right symmetry property.
Right.
Okay, are there any more questions? If not, maybe we can thank Samir again.